Good afternoon, this is Schweitzer. We're going to run through a little video here where it's just general, big idea, intermolecular forces, types of questions you may or may not see on this concept. So you need to come up with how in your brain you're going to think about this concept. You need a decision tree that you're always going to kind of follow. Now, it is a couple different versions of that someone might think about this. I would maybe split it into two versions here. The first one is, the way I generally look at this, again, is, okay, the first thing I look at is, do I have a highly electronegative atom? This is my thought process. NOF. Do I have one of those? The main reason for that is because when you move into organic chemistry, which is the next step beyond this class, that's kind of what we're looking for. If you have a molecule, and some of the molecule you have one of those guys, you have a hot spot, which is going to cause polarity, which causes property changes. And that's how I was sort of trained to kind of look at this. You could have a detergent molecule which has got really long string chain, and then it's got a hot spot on the end, which this helps dissolve nonpolar substances. This is a part that dissolves polar substance, and it's a great molecule. It's in, if you look at this molecule, it's in everything from toothpaste to everything else. We have detergent type molecule. Okay, so that's how I do it first. I say, okay, now again, some of the AP questions this might not lend perfect for. The reason why is because, okay, well, when I do this here, I kind of branch off. I say, okay, well, if I have one of these, then I'm going to have, potentially, if it's yes, then I'm going to have, an option for one or two different things. The first one's going to be hydrogen bonding and or a dipole-dipole. Okay? That's how my brain works, okay? If the answer is no, then my major force here is London dispersion forces, okay? And of course there are factors that affect the strength of that, which is going to be long chains, okay, and number of electrons. Now the key word I meant to say there was major force. If you don't have one of these, could you still have one of these guys? I would say hydrogen bonding, typically the answer would be no. So hydrogen bonding really is a specific force where you have one of these guys hooked to hydrogen, and that would be hydrogen bonding. Okay? But of course, hydrogen bonding is just a form of dipole-dipole. So if you don't have one of these things, then can you still have a dipole-dipole? And the answer is yes. Yes, absolutely. Okay? Can you have this? Yes. So what's going to happen here is they're going to give you a series of data. And one of them might be, they'll have a little quantified amount of a dipole moment. And of course, dipole moment. Now, if they ask you, list every intermolecular force listed, unless you have a dipole moment of 0, then you have to list it, and that's the problem. Okay, you can't just ignore this that it's not there. Only way to have this not be present would be have a dipole moment of 0, and we'll talk about that down here. And keep in mind, London dispersion forces, even if it's not a major force, it's always present. So they could have a column describing mathematically dipole moment, and they could have a column measuring mathematically polarization, which is describing this London dispersion forces. And of course, if you have a substance that has one of these highly electronegative atoms, then this is going to be driving through the roof, and depending on the molecule, we don't know, this thing could do whatever. And they're going to ask you to explain why the dipole moment is so large. And any fact, and you could have another one here that just has the boiling point. And you could say, relate the dipole moment to the boiling point. Or if we don't have one of these things, maybe there's still a dipole moment, but this thing is driving through the roof, and they want you to explain why this thing is affecting the boiling point. So it's always there, and they want you to pick and choose between them. Okay. This is classic advanced placement style stuff. So you can choose to think about it like this if you'd like. But someone else might say, okay, I'm going to choose to think about it this way. I'm going to start with dipole moment. Dipole moment. Okay. Do we have one? Yes. Or do we not have one? No. Okay, that is kind of important. Because now, if I have one, well, first of all, how do I have a dipole moment of 0? Well, if it's symmetrical, okay, or if the elements are identical elements, okay, electronegativity. So when you subtract the two, and a lot of times if they're identical, well, then guess what they are? They're symmetrical. So lots of times symmetrical is really something in AP land that they're really looking for you to discuss. Notice I didn't mention it up here, but it would be involved right here. Okay, it'd be a way to cancel it out. So this might be an alternate thought process, or if you get good at it, you just bounce between the two. So do I have a dipole moment? Yes or no? Okay. So if the answer is no, then you got to be able to explain why the only thing you have possible to you is London dispersion forces. And of course you'd want to discuss the factors that affect London dispersion forces. What if the answer is yes? Okay, well then of course we have the possibility of hydrogen bonding, and we have the possibility of just a plain old dipole-dipole. But at some point, you need to be able to discriminate between, yes, I have this, but are they significant? Okay? What is the level of this? The level of that. And mainly just that one, because of course we already discussed that hydrogen bonding is very specific right there. Is there a significant level, or is there not a significant level? Okay, but that's fine. You just need to discuss all that's present and just be able to describe why you wouldn't. Let's say this is low. Okay, you have a dipole moment. It's just not real big. Well, then you might have to explain why the London dispersion forces then maybe is causing an issue. Okay, or why they're both low. Okay, and therefore why that's affecting the boiling point or the melting point. Okay, so this is another way that someone might think about this, and you need to be able to understand both ways and or have some way that you're wrapping this into your noggin. Okay, huge concept right here. Okay, so next idea here. Molecular shapes and number of forces. Okay, so again, we're just throwing some general thought process. We just talked about this. All right, questions. What type of substance is it? What type of internal forces are present? What would I expect to have a higher melting point? Would I expect the substance to dissolve in water to a large degree? Now, this last one here, on this last page, a couple things you should remember here is that these two guys here, this guy is polar. Okay? So this is going to affect things like dissolving. Okay? In a polar substance. Polar solvent. Like water. This guy here is nonpolar. And this is something that is going to be dissolving in, let's say, nonpolar solvent. Nonpolar solvent. So in this situation, something like, I don't know, common one might be like hexane. Hex would be 6, C6H14. Okay? All just a carbon chain, nice common, okay, one more carbon I think there, solvent. So, alright, so just a couple things as we walk through here. What are my general thoughts about this? As you look at these molecules, you should automatically start thinking about the shapes of the molecules and what they have. So let's take a moment just kind of jot down what I think about these molecules. I think, let's see, we got it. Well, we'll do this in the next couple pages. Okay, so let's look what we got here. This guy right here, okay? Again, you need to be able to do this without me showing you these answers here. So let's kind of back up here for a second, just kind of see what I think about this guy. I'm going to walk through each one here. We'll just kind of just give it some general information, then I'll run through those pages. Alright, so first things first, CH4. You should note that carbon follows the octet rule to a T. Okay. This guy, therefore, is symmetrical. Okay. And the only thing we're going to have that again, dipole moment of 0. London dispersion forces, and it's going to be low. So immediately I'm kind of bouncing between my thought processes. I don't see a highly electronegative atom, but I'm symmetrical, so I only have this. This guy looks like this. Okay, it's asymmetrical, note the unbonded pair there. So this thing is going to be a classic example of hydrogen bonding. It would be polar and would dissolve nicely in water. Does it have London dispersion forces? Yes. London dispersion forces is a yes as well, because it's a yes for everything. But based on what we have here, it's relatively small. This guy, alright, it's NH4+. Okay. Now this thing is symmetrical. So, can it hydrogen bond? No. This thing has London dispersion forces really only, but it does have a positive charge. The whole thing has a positive charge, so it can act like a cation. That's important to realize here. This is called ammonium. And as a cation, it does dissolve nicely. This is a charged particle. It will dissolve nicely. It will form ion dipole attractions to water. Okay, so this is another unique situation. It's got a positive charge. You should be aware of how that's going to work. Another classic example would be carbon dioxide, and you should note that its structure here, roughly sketched, is symmetrical. So because it's symmetrical, it has canceling all dipole moment of 0, and all it has is London dispersion force, and they're relatively small only because this is a relatively small molecule. I would expect this to dissolve in water minimally, which of course it does. You can see this in carbonated beverages and things of this nature, but sometimes they need to increase the pressure on it to really get good amount dissolving. As soon as you open the can, the gases come out. Alright, so this next couple pages are just going to walk you through some of these things. So, ion molecule network, what is this thing? It's molecular. And you should be aware of that, all nonmetals. What type of intermolecular forces are present? Do we have London dispersion forces? Yes. But they're weak. Dipole-dipole? Yes. In fact, the version we have here is hydrogen bonding. Okay. Note the shape. Asymmetrical. Let's see our final thoughts here. NH3 exhibits hydrogen bonding, therefore I think this substance might be a liquid or a solid at room temperature and would likely dissolve nicely in water. So it's got some hydrogen bonding, so depending on the temperature, it could end up being liquid. NH3 itself is ammonia, NH3. You could have ammonia gas, okay? Smells badly. It smells like kind of urine type smell. So you definitely debate, it's definitely volatile. When you put it into a jar, like liquid, it's definitely going out, yes. Pure ammonia, vaporized nicely. Kind of talked about this one already. Again, I summarized things London dispersion forces. Yes. Dipole-dipole. No. No. This one I might call it both molecular and ionic. It can take part in ionic bonding. Okay. So look for that. Ion dipole sort of stuff. CH4, so a little order here. Alright, what is this thing? It's just straight molecular. London dispersion forces, yes. Let's take that arrow off of there. Ooh, yes. But it's going to be small. Very low polarizability because of its amount of electrons and stuff of this nature. No, and therefore no. You can't have hydrogen bonding without this. That's the same thing. It's like final thoughts on CH4. This thing really is a gas, right? It should be a gas. This is one of our main components in natural gas. And you'll note that if you have a house, okay, and you live out in the country, that you might have a tank sitting outside your house.
And that tank is going to contain C3H8, which is propane. So propane has a long enough chain to have enough intermolecular forces that with a decent amount of pressure I can condense this to a liquid, which therefore you get a higher density of material in the liquid phase. Gas phase, not very dense. If it couldn't be condensed to a liquid, the tank itself, if it had a gas in it, man, the only way to really get enough stuff in here to make a difference to heat your house, the pressures would need to be enormous. The fact that this stuff condenses to a liquid makes it easy to transport and a much, much higher density fuel. This is sometimes an issue with cars. I mean, how can you get enough energy density to store a gas as a car for fuel? So anyway, so the propane's the first one. If you're using natural gas, you will find you don't have the tank. What you do have is a pipe underground. All right, it's probably an inch and a half pipe, and it runs in, and it only carries gas, and the gas just pumps every your house. They actually use underground old salt mines to hold all this gas. So they have unusual ways of storing this stuff. All right, God, I digressed there a little bit. So, methane. All right. So what do we need to know about inward forces' effects on properties? This simply is a relationship involving Coulomb's law in the form of IMFs. Two properties are the most commonly tested on the AP exam: solubility and melting point. So make sure you're aware that on this thing, what about solubility here? Well, okay, that's an important concept here. So when something dissolves, it has to, the polarity is what's causing this thing to dissolve. Polarity. Okay, so when you have a polar solvent, you need to be polar to dissolve in it. So there's an old term, likes dissolve likes. We don't really want to use that. You want to talk about one polar substance attracting to another polar substance. Okay? Again, you could be hydrogen bonding, or a dipole, or ion dipole. And of course, we'll do lots of examples where you have to draw this out, where when you have a water molecule and you have to be able to show some item attracting to it. So this is the negative end, this is the positive end, and we use dots to show this attraction. If you only have London dispersion forces, or your level of dipole moment is very small, then your dissolving in water is going to be very small, and that's a big concept that you're going to want to understand. This ion dipole would be more for ionic compounds. Keep that in mind. So that's something you really want to have under your belt. Melting points. Okay, what breaks? This is a really important, because if you have a strong bond, the stronger your bond is, then the higher the melting point. So let's say for a network covalent, in a network covalent, you're breaking a covalent bond, like in a diamond, for example. So this is really high melting points, highest you'd have. Ionic compounds would be next, ionic. Okay, and then of course we have a breaking point where we're doing molecular. So you have things like hydrogen bonding, and just dipole, or various London dispersion forces. Okay, so you really need to know what breaks when something melts. And sometimes that will indicate the size or the magnitude of the melting point or the boiling point. All right, weaker bonds, okay, they're more easily broken, so they have lower melting points. Pretty important concept. All right, so properties, compounds, polarity, determination of resulting consequences. Okay, only one here that again that kind of a re-summary of this thing. Increase intermolecular forces and or bond, okay, bond type. Increase melting points. So if you only have the things holding it together are just weak London dispersion forces, then likely a gas. As you go up here, if the thing holding together is covalent, like I'm not talking about like water here. If you have a substance where the substance is actually held together by covalent bonds, we call that network covalent. All right, network covalent. Then, you know, this thing's going to have super high melting points. So what breaks when this thing melts? Vapor pressure and solubility. So this is a new one I'm going to add here, okay? So if you have a substance which has increased intermolecular forces, then as a liquid, it's going to be less likely it's going to want to jump off the surface. If I close this container off here, you'll find that you're going to get a certain amount of gas going, and then it's going to start returning back. We call this vapor pressure. Okay, get it right here. You should note that as you increase the intermolecular forces, the vapor pressure goes down, and vice versa. The more this guy can stick to another one of these guys, the less likely it's going to be able to jump off the surface, and therefore you get overall lower intermolecular vapor pressure above here. You should also realize that if I increase my temperature, my vapor pressure also goes up. I get they're moving around more, so that this breaks easier and it's able to get up here. And I end up with an equilibrium state of a much higher level of pressure as I raise my temperature. Okay, so how does AP ask questions relative to bonding and intermolecular forces? This is a great question here, just to kind of give you an idea how this works. Now, as soon as you look at one of these things, you should automatically, your brain should be, automatically be thinking, about how did I organize those thoughts about bonding here? They're showing you a shape, they're giving you some data here. And so we're looking here, this one's high, this one's low. Sometimes they'll have data that matches what you think is going to happen. Sometimes they'll do contrary, and you need to kind of to be able to discriminate. Data can match you think, or data can be contrary to think. So you need to be able to rationalize either way. It's correct because this is what's happening, or it's incorrect because this is what's happening. So when I look at these things here, again, how you think about this is different. Okay. First things first, they're giving you a shape. So this thing I see is symmetrical. Dipole moment of 0. Okay. So now the only thing you should be able to rationalize, what's the only force that you have here? If it's symmetrical, the only thing you have is London dispersion forces. All right. Next one. All right. I have, looks like I got a carbon. I have all the carbons here. The sulfurs. What's we got here? Carbon is black. This is sulfur, and this is oxygen. Okay. All right. So what I see here, when I look at this, oh, okay, I'm straight. But I got the oxygen on the side here, which is one of my highly electronegative atoms. Even though he wrote the oxygen in the center, I don't think I screwed that up. Sulfur, carbon, oxygen. This thing is going to have a dipole moment for sure. Okay. And I think it's going to be a little more of a significant dipole moment. Dipole moment. All right. But now look at this. Boiling point. For some reason, this one is higher than this one. Okay. So now, as I'm looking at this data, I think, dipole moment. This one should have a higher boiling point than this one. This one should be lower. Yet what I'm thinking here is contrary. So therefore, because this one's higher means only one thing. And that is that for some reason, well, not just for some reason, the London dispersion forces are a factor here. And this is driving up that melting point. And of course, you'd rationalize, what are the reasons why London forces gets larger? Long chains. And increased number of electrons for what we call polarizability. Okay? So now you have the whole thing kind of wrapped up before we even come to our questions. This thing's got apparently a decent amount of London dispersion forces because these are some larger atoms. Okay, this thing here, even though it has both a dipole moment and it's got London dispersion forces, neither of those are big enough to cause enough attraction to drive up the melting point, or the boiling point beyond this guy. Okay. All right. So this is all the stuff that I kind of went through here. What are the types of substances? What type of intermolecular forces are present here? What's this data telling you? I kind of walked through all of this already. Okay. And this is stuff you want to think about before you even see. This just should snap right in your brain there. Notice that here I put dipole, not hydrogen bonding. Okay. Okay, so here's the question that they actually asked. In terms of relative strengths of all intermolecular forces, each compound, explain why the boiling point of CS2 is higher than COS. And I kind of talked about this already. Here's a written version of this. Okay. Now here's one thing you want to really be careful of. They're actually asking you to compare both items. What if you only discuss why this thing has increased London dispersion forces? Then you're only going to get +1 for that, and then you're going to get -1 for this guy. They expect you to discuss both items. Okay? You have to discuss both items because the rubric will involve both items. It's going to be worth 2 points. Hint, cover up your question. Can you determine the question from your answer? Write your answer in the space below. So we're going to practice this a little bit here in class. Okay. All right, here's another example. Now from this thing, again, what do I notice here? Going through my own ideas. First of all, this thing is symmetrical. Okay, dipole equals 0. Okay, do I have London dispersion forces? Yes. Is it higher? Well, it's kind of looks big. None of these guys are really huge, but it's got lots of items here. All right, so what do you want here? So it's nonpolar. It's not polar. It's nonpolar. Benzene. Okay, has a structure shown above. Considering the observations that benzene is only sparingly soluble in water, which of the following describes intermolecular forces of attraction to water to benzene. Again, because I don't have any of this guy, then I would expect my polarity, to be essentially nonpolar, right? Nonpolar. So why would there be an attraction to water? There's no charges, no partial charges to attract to water. So I would expect this to be minimal. Let's see what we got here. So benzene's nonpolar. Therefore, there are no forces attracting. That looks pretty darn good. Let's see the rest of them. Hydrogen atoms in benzene form hydrogen bonding. No. Benzene hydrophobic in water. There's no net repulsion. I don't see how that answers our question. Dipole induce. Yeah. Okay. So here we go. Classic question. This is your typical setup for one particular item, and that is going to be, don't even got to read this. Okay, hydrogen bonding, that's what that is. Thank you very much.